লাগবে না, আমি এতটা করে এখন আসিনি তো কেউ, স্যার আসবে, স্যার ঢুকলো না কেন এবার? প্রবলেম হচ্ছে, আজকে যেটা প্রবলেম হচ্ছে আইএসটি শিবপুরটাকেও লোকেট করছে অন্যভাবে। এসে গেছে, এবার দেখো দেখেছো? হ্যাঁ দাও, তোমাদের দেখাচ্ছি, এবার দেখাচ্ছি গল্পটা কী হয়েছে, এবার বুঝতে পেরেছো? এবার ঠিক আছে, ওই জন্যটা হচ্ছিলো, তাই আমি বলি যে একটা গড়বড় আছে।
Good afternoon. We have assembled here for the second Ramanujan Memorial Oration at Iiests Shivpur. I'll request all of the audience over here to kindly switch off or put their mobile on silence mode. And I will now request our Honorable Director, Professor Ajay Kumar Rai, and today's our speaker, Mahan Maharaj, to be on the dais before we start the program. Thank you, sir. At the outset, we would like to felicitate our honorable guest today and our director. I will request the Assistant Secretary of our Student Senate, Shankodip. Are you around? Arnav. I will request our research scholar Ramanujan Rai, please come forward and felicitate our honorable director. Shankodip, where? Oh, Shankodip. Sorry. Yes, come Shankodip. To felicitate our honorable director, Professor Ajay Kumar Rai. This is the second Ramanujan Memorial Oration that is being organized at Iiests Shivpur. The first one in 2016, the speaker was our beloved Professor Ashok Kumar Mollik. And today we have Mahan Maharaj, Professor at TIFR Mumbai. He happens to be one of the students of Professor Ashok Kumar Mollik. Before start of the program and introduction of the speaker, in some details, I will request our Honorable Director, Professor Ajay Kumar Rai, to say a few words on this occasion.
Very good afternoon to all of you, my dear students, my colleagues from Iiests Shivpur, and some of the distinguished guests. We are extremely happy that today we have in our midst one of the greatest mathematicians of our times. Here with us, Professor of TIFR in the School of Mathematics, Mahan Maharaj, whom the entire country in one word recognizes as one of the very eminent and brilliant minds of today. As you know that in this institute we had started a series of such memorial lectures. These are all very important institute lectures in which one of the lectures is based in memory of one of the greatest mathematicians that the world has ever produced, Ramanujan. And many of you might have read the book, at least the book written on the life of this great personality of 20th century, who did not live long, but his contribution had been simply phenomenal. And as Indians, we all are so proud that this country had witnessed the emergence of such a great mind of 20th century. He was one of the youngest FRS in the whole world, and his lifespan was too small. We can only imagine what could have been his contribution if he would have lived a little bit longer. And to talk about Ramanujan, and especially to give an oration in memory of Ramanujan, who can be the better person than Mohan Maharaj, who is again one of the most eminent personalities in our times. I will not take much time. I will not really want to waste time and be in between Mohan Maharaj and you. But a very few observations can be placed here, because Ramanujan was a phenomenon. And as many of the greatest personalities of 20th century, mathematicians, scientists, had observed that he was a phenomenon which could not be explained. And as you all know, you may not know also that during the last days of Ramanujan, when he came back from England and when he was constantly changing his residence in Madras, and he was very, very restless in a sense of, because of his health condition. Yet whatever little scholarships he used to get from Hardy those days, he used to spend a small part of that scholarship in giving stipend to some of the poor people of Madras in his locality. This fact is not very well known. That way Ramanujan was not only one of the greatest mathematicians, but he was also one of the great personalities, a human being those days. A very little amount of scholarship which he used to get, and with which he had to survive. Those days, you know, the cost of the medicines itself was quite high. He had to look after his wife, his mother, and he never forgot to timely send the scholarship to the poorer class of the society. And that was the greatness of Ramanujan. So we are indeed very happy that we also have got amongst us Mohan Maharaj, who is not only a great mathematician, but at the same time a truly Mohan personality, a great personality, who had renunciated so many things, not like us. We are always after material wealth. But he was indoctrinated, and he is still following the ideal path of the glorious vision of Swami Vivekananda. So we are very happy, extremely happy that today we have got with us such a great personality. So on behalf of the students, the faculty members, the staff members of this institute, I welcome this great professor of India, and I wish very bright and happy days ahead, so that the science of mathematics also gets enriched with his brilliant contribution in the days to come. Thank you.
Thank you, Professor Ajay Kumar Ray. I also do not waste much of the time before we can speak from Mohan Maharaj, but it is my humble duty to introduce our speaker formally. Mohan Maharaj did his integrated masters from IIT Kanpur. He joined there with a bachelor's degree to pursue a bachelor degree in electrical engineering, but his passion for mathematics, he shifted his study from electrical engineering to the specialization of mathematics, and instead of BTech, he did the integrated MSc in mathematics from IIT Kanpur. Thereafter, he had the chance to work with a very eminent mathematician in UC Berkeley for his PhD, came back, joined the Institute of Mathematical Sciences in Madras. Thereafter, his inner call, inner passion took him to the Ramakrishna order, Ramakrishna mission. He joined. His monastic name is Swami Vidyanathanandaji. So he served in the Ramakrishna mission, Vivekananda University, as Dean of Research and Professor of Mathematics at Belur Math. In course of his research, he has already got several accolades and recognitions. 2011, he got the Shanti Swarup Bhatnagar Award. 2012, Fellow of the Indian Academy of Sciences. 2014, he got the Sir J.C. Bose Fellowship, and in 2015, he got the Infosys Prize for Mathematics. So, he has a lot of recognitions, and as Professor Roy mentioned, he is one of the most eminent mathematician in our country today. And thereafter, from 2015 onwards, he is serving as Professor of Mathematics in the Tata Institute of Fundamental Research. He came all the way from Tata Institute of Fundamental Research because of our invitation. We considered him for the first Ramanujan Memorial Lecture also last year, but because he was busy with some other engagements, he could not come at the time. So we are fortunate that this year he could accede to our invitation and came over all the way from TIFR. And I will request now Mohan Maharaj to deliver his lecture before all of us. Thank you.
ওনাকে নিয়ে আমরা প্রেজেন্টেশনটাও রাখতে হবে।
মাইক লাগবে না।
Okay, so thank you very much for this very kind introduction. Problem with introductions which are too kind is that one is always afraid that the talk does not live up to it. But I'm not guilty for that part. Okay, so all right, so let's. So there was an announced title of this talk, and that there is a slight discrepancy between that and the title on the slides. Yeah. So the title that was announced is short, Geometry and Chaos. And I think the title, I mean, these were slides that were ready, and I did not change the title page to Geometry and Chaos basically because of laziness. Okay? So anyway, so what kind of geometry is we will say what this is, what hyperbolic geometry is about, and what kind of chaos. It's going to be chaos of a particular flavor, chaos on the complex plane. Okay? So this is supposed to be a popular lecture, so I mean not particularly technical. So I'll start off with an example of what we regard as hyperbolic geometry occurring in nature. Yeah, mathematicians are a somewhat odd breed, so their idea of what constitutes natural objects is not entirely in agreement with what other scientists and engineers call nature. So I'll start with a fairly non-controversial example of what constitutes a natural example. Oh boy, this is not moving. Okay, so I'll start with No, it's fine. I think it's just slightly. Okay, fine. Never mind. All right. So I'll start with a fairly non-controversial example of an example from nature. So a tree is probably the most visible example of something that demonstrates hyperbolic geometry. I mean, functioning in our three-dimensional Euclidean space. Why and how this is hyperbolic geometry in action is something that we'll explain as time goes on. Okay? But the geometry of the tree, the underlying geometry of the tree is not entirely visible because it's covered by the foliage, by the leaves. So what we do, I mean, this is a mathematician's attempt at getting at the underlying geometric structure. So we strip away the foliage, and then the geometry starts revealing itself slowly. But even this is too much information, so we try to simplify it further. And here we have something that we can put on paper, something that is an example of what we call mathematically a tree. But even this it's got an aesthetic appeal certainly, but the bare bones mathematical structure is still not clear. So we simplify this further. And this is a two-dimensional representation of a tree. I'll just draw your attention to one of these, one feature of this picture here. It's that all the edges of the tree, say the stem and then the branches that go off from it, the branches that go off from the stem are shorter than the stem. Yeah? Then once the branch starts bifurcating again, the branches become smaller. Those branches start bifurcating and they become still smaller till at the end they're extremely small. Yeah? This structure of something going on bifurcating, yeah, it's called a regular dyadic tree or two-adic tree, which means or a regular three-adic tree, which means that every vertex there has valence 3. There's one incoming branch, two outgoing branches. Every point has that nature except for the base. Yeah. All right. So yeah, let me just draw your attention to this one feature of this particular geometric object, which is that as you branch out, the branches become smaller and smaller. If you look at a tree outside, the same thing happens. The stem is long, the branches become shorter and shorter, till you have leaves, and inside leaves, the branch goes inside, right? So there's a main, I don't know what, yeah. So there's a main channel through which water is supplied to the leaves, and then those branch out, and then finer and finer tendrils start cropping up, right? There is a reason. I mean, just try to imagine that this huge amount of division, if the stem was the same size as the branches that bifurcated from it, and those branches were the same size as the branches that bifurcated from it, what do you expect would happen? The trees are actually pretty intelligent creatures. I mean, so they are really trying. What are they trying? Why? What is the physical reason? I mean, the natural reason behind this bifurcation. What is the tree trying to do in getting to this collection of leaves? What it's trying to do is it's trying to maximize the surface area that is exposed to the sun, right? That's supposed to be by which it catches its energy. Yeah. All right. What will happen if you have something that does the opposite, tries to minimize surface area. So you take, say, a blob of some liquid, yeah, and allow it to, so suppose you are in a vacuum, no other forces are acting, and it tries to minimize surface area. What are you going to get? Yes, please speak up, yes? You are going to get a sphere, correct. So, what are you going to get if you try to maximize surface area? That's what the tree is doing. Yeah? So the sphere is something that draws everything. So basically, most of it is inside. Yeah, that's what the spherical shape captures. What the tree is doing is exactly the opposite. It's trying to maximize the surface area of contact with the outside. Whenever you have some such phenomenon happening, a maximization of n minus one dimensional volume with respect to n dimensional volume. Here it's two-dimensional surface area with respect to three-dimensional volume. Yeah? You're given a certain amount of mass, that's your three-dimensional volume. You're trying to maximize the two-dimensional surface area that it bounds. Then it is going to immediately, I mean this is a certain meta theorem that as soon as you have some such thing, it's not quite a theorem because of certain technical reasons, but as soon as you have some such phenomenon occurring in nature, what you will have is somehow hyperbolic geometry in dimension 3 with a certain other kind of geometry on the surface. Yeah? So I have this picture here. This is in some sense a one-dimensional geometry. So if you look at that tree there, you look at a point on it, suppose you're a creature living on that tree, yeah, and you don't have another universe outside of that tree. So if, say for example, an ant creeping along that, yeah, it's going to see only a one-dimensional universe, right? So the object that we start off with, yeah, is a one-dimensional object, but the boundary, what is happening at the boundary, technically what is happening, I mean, you see a lot of, actually, if you pick up only the tips of all those very small branches there at the end of the tree, you're going to see a collection of points which have some fairly interesting structure. Yeah? It looks like dust, in some sense. A lot of dust particles, all on the, it's here, I mean, you just take this point, I mean, all these points, all at the end of the tree. Yeah, it's like a collection of points. Points are zero-dimensional. Yeah. So what I'm trying to illustrate is that in this kind of a picture, you have this one-dimensional geometry, which I have said is hyperbolic with no explanation why it is called hyperbolic, but with a certain other kind of geometry on the frontier, which is in one dimension less. So here it's zero-dimensional geometry on the boundary of a particular kind with a different kind of geometry in one dimension higher. Yeah? So what is that geometry? If you look at a tree, if you look at the surface of a leaf, of a tree, the foliage, it's extremely crinkled. Yeah? In some sense, what is happening is, if you take one of these branches and cut it off, yeah, just chop this off here. Now scale everything by a factor of 2, let's say 2 or 4 or something. You're going to get back this whole tree. Yeah. So suppose this branching is going on infinitely often. Yeah. Assume that the branching is infinitely often. So now you cut off this, and then you scale the whole thing by a factor of 4. Yeah. So this piece chopped off, scaled by a factor of 4, is going to give you this whole picture back again. Right. So, and you can do this at any scale. You go down to a very small scale, and then you take this little floret here, chop it off, scale by 2 power n sufficiently large, you're going to get back the same picture. Yeah? This feature of an object where certain features are replicated at all scales is called a fractal. Okay? So this is a certain name. It's a technical name. It has a certain technical meaning which I don't want to go into, but for the time being, what I want to just insist is that there is this zero-dimensional dust. It's got a particular name. It's called the Cantor set. Some of you will definitely be familiar with this. Yeah. What do? You take the interval from 0 to 1, closed interval from 0 to 1. You take the middle 1/3, from 1/3 to 2/3. and remove the interior, throw it away. Now you have two intervals. Yeah? You remove the 1/3 here, remove the 1/3 here, and throw it away. Now you have 4 intervals. Remove the 1/3 of all those. Do this infinitely often. Yeah? The intersection of all these things, finally you're going to get some dust. Yeah? That dust is called the Cantor set, and that's really what's going on at the boundary of this tree. Yeah? So this Cantor set is the simplest example of a fractal. It's in dimension 0. And it does appear as the fringe of a one-dimensional hyperbolic gadget called a tree. What a hyperbolic gadget I have not said. I've said something about how a fractal comes in so far. So you'll have to do that. All right. Let's get to, so one feature that you will see here, as I've drawn your attention already, is that the stem becomes half in size and then that becomes further half in size and so on. What would happen if we tried to draw all these guys to be the same length? This is a certain problem that I'm asking you to think about. If the tree tried to do it, very soon it would become extremely congested. Yeah? So, it's a theorem due to Hilbert from 1900 or thereabouts, which says that this can't happen in three-dimensional space. Yeah? There's a certain very specific reason, mathematical reason, why the size of a branch and the size of a stem on a tree are not the same. Yeah? If we lived in a space which was intrinsically hyperbolic, I'll come to what that means a little later, then the tree would be able to branch with all stems and all branches the same size as the same size as each other. Okay, so now let's try to get to a picture where the size of the stem and the size of the branches are the same. Oh boy. Okay, so this is an example. This is an example of what is mathematically called a tree. It's a graph. Yeah, you have a bunch of vertices, the black blobs there. These are joined by edges. The edges have length 1. So normalization we fix. So what is a graph? A graph is a collection of vertices, black blobs, joined by edges, all edges of length 1. Now, if there are no closed loops in your figure, then it's called a tree. Yeah? So this is an example of a tree in this formal mathematical sense. And an informal way of describing what a hyperbolic space is to just say that it is tree-like, yeah, in a certain sense, which will be made formal slowly. Yeah? Okay? But for the time being, I just want to sort of fix notions. I'm just giving this picture. This phenomenon of n-dimensional hyperbolic phenomena versus n-1 dimensional fractal phenomena, yeah, that here we have illustrated in the simplest case where you have a one-dimensional tree and a zero-dimensional Cantor set or fractal boundary. This phenomenon is not specific to one dimension versus zero dimension. It's ubiquitous in nature. So here you have an example of either a sea anemone or a sponge, and what's happening here is the same thing. You have, I mean, each of these, if you look at one of these gadgets here, yeah, it's like a disc, it's a cup, right? And the water keeps flowing past the cup. This cup actually captures its food from the surrounding water, yeah? And it wants to have maximal surface area of contact with water, which means that the disc, the sponge, what is it trying to do? Each component disc is trying to maximize the surface area of contact with water. What happens as a result? Look at the fringe. The fringe is actually topologically, it's just a circle. Yeah, it looks just like a thread which is taken around in an extremely wavy way and comes back to where it starts from. Is that clear from the picture? There is this picture of a circular loop here, yeah, and it's bounding a disc, right? The disc is trying to maximize area, so it has intrinsic to it certain geometry which is hyperbolic. The boundary, which is this one-dimensional circle, is extremely wrinkled. Yeah. So this is an instance of a two-dimensional. What does maximization of surface area do? So many of you, what is the simplest example that you have seen outside? This is exactly the example of a horse saddle. Yeah. So if you have a saddle on a horse, yeah, around on top of the trunk of the horse, it goes upwards. Yeah, so the curvature is pointing into the body of the horse. Yeah, but the person sits in along a line which is curved in the other way. So the normal to the normal to the surface, one points upwards, one points downwards. Correct? You have these. Yeah. Then let me draw it. It's okay. Okay, thank you. That's fine. Okay, so yeah, you. All right. Okay, so you have no. That's fine. So you have. I mean, in any case, I'm not a particularly good artist, so I won't be able to put a book. So imagine the rest of the picture. Okay, so what's happening is, so this is in the this is the x, and this is the z direction. This is the y, and this is the z direction. Yeah. So you have, say, a parabolic curve in the xz plane. The normal is pointing upward. Yeah. So this is curved upwards. Now you look at the z plane and this is your y axis. So you look at the y-axis coming out of the board. So this is, and then you have this curve coming out of the board. The curvature, so the normal direction to that curve is pointing downwards. You interpolate some piece of paper between these two curves, you get the saddle of a horse. So it's curved this way upwards and this way down. Right? Okay. So at that point, at the saddle point, yeah, you have two normals to the surface in opposite directions. That's an example of what is called negative curvature. Yeah. So now you look closely at this disc of the sponge, and you look at some point here. What is happening is that there is some curvature that is going in this direction, and the other one that is going into the plane. Yeah. So every point is trying to the curvature that it's trying to trap at every point is negative. Yeah. Why? Because that's the only way it can maximize surface area. For instance, try to do this experiment at home. Take a bunch of equilateral triangles, same size. If you glue 6 to a vertex, you're going to get the flat plane. Instead of gluing 6 to a vertex, try gluing 7 to a vertex. So then it's going to become extremely floppy, and the boundary is going to become extremely wrinkled like this. Yeah? That's an illustration of negative curvature bounding a one-dimensional fraction. This happens in our human brain. The neurons are trying to divide very fast, yeah, and then it develops an extremely wavy surface. Yeah? So this is three-dimensional hyperbolic geometry versus two-dimensional fractal geometry. Yeah? The surface is two-dimensional fractal. Inside the brain is three-dimensional hyperbolic. Okay? More simpler examples which you can cut is the cauliflower. Similar things happen. Yeah? An artist rendition, and finally I'll come to the most formal part of the talk, the real mathematical part of the talk. And you're not supposed to comprehend anything from this picture except that it's actually quite pretty. So this is from a book called by David Mumford, Caroline Series, and David Wright. The book is called Indra's Pearls. So what is it? There's a bunch of, pictorially and picturesquely called pearls. But what you imagine is that you have a bunch of globes, yeah, which are perfectly reflecting, which means that they are going to allow reflection infinitely many times. Light is not going to disperse. So those are these big blobs here, yeah, and then they touch each other or intersect each other. Now you set up a reflection mechanism, which means what? You allow reflections infinitely many times in these blobs. What's the picture going to become? And as you go around, it's what's happening is that essentially the space inside the room above this blue plane, yeah, that is equipped with a certain geometric structure called the hyperbolic structure. And this two-dimensional plane on the boundary, you should think of that as the complex plane, x plus iy. Yeah? Yes? Is the question? Is there a question? Okay. And please feel free to interrupt me during any time of the talk. I mean, the point is to communicate something to you. So yeah, I mean, yeah. Don't hesitate to stop me. So what's happening is that on this complex plane there is some kind of a fractal structure which is sits in dimension 2, and inside this room there is a 3-dimensional hyperbolic geometry that's going on. Yeah? So this duality is a formal mathematical instance of the human brain. I mean, so of this the body of the brain versus the surface, 3 dimensions versus 2-dimension dichotomy or duality. Yeah? I'll say a bit more about the mathematics that gives rise to this kind of a picture now. Okay. So let's get back. So let's start making formal definitions, more precise definitions. Let's go back to the picture of the tree. Yeah. Suppose we wanted to convert this into a geometric space. What does it mean? I'll have to consider analogues of straight lines and triangles and so on in this geometry, right? So what are straight lines in this geometry? What do you mean by straight lines? Distance minimizing paths. Okay? So take a vertex here, take a vertex here. What is the distance minimizing path? So all the edges have length 1, right? So you just have to have a minimum number of edges from here to here by a path which lies entirely on the tree. I can't draw this straight line across because this space is not available. Yeah? So I am an ant living entirely in this tree. Yeah? That's how one thinks about it. So what is the shortest path? Anybody? Yes? Go ahead. Yeah, which is it? That's right, very good, excellent. I wanted somebody to do this. So yeah, so it goes all the way down here and comes up, right? That's the shortest path. So the shortest path, which joining this point and this point, this guy is the analog of a straight line for a creature living entirely in the tree. Clear? So now for given any 2 points on the tree, we have straight lines, and for a tree that straight line is unique, as you can see from this example. I mean, take any 2 points here. There's going to be only one edge path which does not retrace itself. That's the shortest. That's the analog of the straight line in this geometry. Yeah. So any 2 points are joined by a unique straight line, like in Euclidean space. Yeah. All right. What about triangles? And now I think I'll have to draw a picture again. So let's pick up three points here. So you have A here. This is your B. The first point is A, the last point is B. Now I pick up any other point, say this guy, some point C here. And you have this. So if you wanted to join, so let's say A, B, and this point here is C. Yeah? So I want to join C to B. Similarly, what will happen is that you will have to take a path till you hit the edge, till you hit the path joining A to B, go down there, and then go along B. Right? So this path followed by this path is the analog of the straight line joining C and B. Similarly, what is the straight line joining C and A? You go down here and then all the way here. Right? Okay? So then what is the analog of the triangle? So now let's try to draw this in the way we are accustomed to drawing triangles. So you have a straight line between A and B. You have C here. The straight line between C and B goes down, hits AB, then goes here. Right? The straight line between C and A goes down till it hits this and then goes along this. Correct? Right? So the triangle with A, B and C as vertices looks like an inverted T or a Y. Okay? All these letters give the same thing. What feature is there of this? What geometric feature in such triangles distinguishes it from triangles that we are accustomed to in Euclidean space? And here's the point. You can check this. You look at the side AB, yeah, this is contained in the union of these two sides. Correct? Does it happen in the Euclidean space? Is any edge of the triangle, is it contained in the union of the other two sides? No. Right? Here it is contained in the union of the other two sides. Yeah? So this we want to see. Basically, this area of geometry generalized many things where this was proposed by perhaps the finest geometer alive today, Misha Gromov, the Russian mathematician. He came up with a notion of geometry which would help us do away with the infinitesimal calculations in infinitesimal computations that one needs to do in calculus. Yeah. So basically, to do all these curvature estimates for this saddle connection, for instance, you have to compute this. See, for example, even in high school, you have this formula which is actually quite ugly. Some d2y dx2 1 plus dy dx whole square whole to the power 3 by 2. Entire meaning of it, there's some simple visual information content to it. That's completely destroyed in the formula. Yeah. So this was a way of recapturing that visual information. Geometry is about visual objects. It's not about computations. Yeah. So how to recapture that information and get it back. So there have been other areas of geometry, algebraic geometry, differential geometry, analytical geometry, etc., etc. So this, we like to call it geometric geometry. Okay? All right. So it's basically back to geometry. Yes, please. That is true. But yeah, that is true. But I'll tell you why this particular description is relevant. Yeah. So what's going on here? And this is basically, the reason for Gromov coming up with this thing is basically you allow a person to do geometry if he can see only macroscopic objects. Yeah. Geometry started with Euclid. Yeah. Or even before. So this is 200 BC or more. When did calculus start? 1500 AD or thereabouts, right? So you should not have to have that much sophisticated computational tool in order to do geometry, right? So this is back to sort of what are the gadgets that we use to manipulate straight lines, triangles, angles, etc., etc. So it's trying to go back to that. And therefore, the feature that is here is that one recognizes is that a side is contained in the union of the other two sides. That's some soft information. Basically, you just need the three big objects, right? One way of saying that it is exactly, one way of trying to avoid this kind of a statement that it's exactly equal to some intersection is that we would like some leeway. Yeah? Containment is, you allow some flexibility. If it is equality, then you have to match exactly. So that's one reason why you allow this. Yeah. So now suppose somebody had bad eyesight. Yeah. He was not able to see exactly whether the side is exactly equal contained in these two sides, but he can see with, say, the amount of resolution that a fly's eye has. Yeah. So we may modify this and just say that this is contained in a delta neighborhood of AC union BC. Yeah. Which means what? You take AC, you take a slightly fat thickening of this, take BC, take another fat thickening of this, and you say that AB is contained in that fat neighborhood. Yeah? So basically you want to still be able to do geometry even if your eyesight is not 20/20. Okay? Alright. Good. So this particular feature, this definition which I have tried to motivate here, was made formal by Gromov and said what is a hyperbolic space? This is the formal definition. A hyperbolic space is one in which you have a notion of straight lines. Any 2 points can be joined by a distance minimizing path. Such paths are called, given a name, they are called geodesics. Okay? Analogs are straight lines. Yeah? So triangles, as soon as you have straight lines, you can form triangles. Yeah? So what is a hyperbolic space? A hyperbolic space is one in which triangles are thin. What does thin mean? It means that every side is contained in the delta neighborhood of the other two. As soon as you have straight lines, any 3 points you can join by the 3 different sides, A, B, B, C, A, C, yeah, and then any side is contained in the delta neighborhood of the other 2 sides, yeah. So you can replace A and B by A and C, or etc., etc. So every side is contained in the union of the other 2 sides. What's special about a tree? For a tree, that delta is actually 0. It's any set is the 0 neighborhood of itself. Yeah. So if you have a side contained exactly in the union of the other 2 sides, that is exactly a tree. Okay. All right. So now we've defined one player of the game. So this is the hyperbolic geometry part of the story. Okay. All right. Let's go back to this feature that I had talked about a little earlier, that a tree in Euclidean space has the edges branching off and becoming smaller and smaller as we bifurcate. Yeah? And why is that? I had sort of said that. See, if you look at a Euclidean triangle, yeah, just take a small equilateral triangle for instance, yeah, and you give me a delta. Say, give me a delta. See, this delta can be very large. It's not the usual notion of a delta in mathematics where your delta is typically thought of as small. This delta can be thought of as very large. There has to be just some delta. That could be 10 million, for instance. Yeah, but some delta. Yeah. So suppose you give me a delta. Yeah? Say 1 million. Can you find an equilateral triangle which is not 1 million? I mean, delta equal to 1 million thin? Yes. You take your Euclidean triangle, Euclidean equilateral triangle, assume all the edges are 1 each. Now, you scale the whole triangle by say 10 power a million, right? Some very large number. Then no side is going to be contained in a million neighborhood of the other 2 sides, correct? So, Euclidean space is an example of something which is not hyperbolic, okay? So, Euclidean triangles in general, if you allow scaling, they are not hyperbolic, right? So, what is happening here is that the hyperbolic geometry, which is the intrinsic geometry of the tree, that is entering into a conflict with the geometry of the surrounding space, which is hyperbolic. Yeah? Press the question mark button. What question mark button? ये ठीक है, এটা ঠিক আছে। Okay, so let me carry on at the board and then let this thing come through. And okay. So what's going on in this So in the example of a tree, what is going on is the following, that you have this large edge, then you scale by a factor of 2, let's say. So if the original edges were of length 1, the next set of edges is of length half. Yeah, this bifurcates off, becomes 1/4, this becomes 1/4, and so on. So this is 1/2, 1/4, then this bifurcates 1/8, and so on. Yeah. What is the length of this total thing? It's the geometric series, right?
Yeah.
Plus 1/8 plus so on. So this is equal to 2, correct? So if you look at the shortest path, but which is now infinite, wow, great, excellent. Thank you. So now let's come back to that tree, and you take the edge path along from the stem right till the tip of the tree, that has finite length. Yeah? And so what the boundary points, actually if you look at this series here, it's an infinite series. No finite sum is equal to 2, right? The infinite sum is equal to 2, right? So the sum is always increasing and it's trying to accumulate to something which is equal to 2. So this point where the distance 1 plus half plus etc. is actually equal to 2, yeah, is really at infinity of this space, correct? If you think of some guy sitting on this tree, so there are two features that I'd like to think of like you to think of simultaneously. One is a case where this tree has every edge of length 1, right? That cannot be pushed inside Euclidean space. That is the intrinsically hyperbolic object. Now we hit it with this Euclidean perversion, where each edge is now scaled by 2 power n as if the edge was at distance n from the original guy. Now it's fitting inside, right? But then it's not a complete thing. You can try to complete it, and there is some space at infinity. That space is like dust or a Cantor set. Okay? I said what a Cantor set is. Cantor set is an example of something which has the structure which replicates itself at all scales. So through this path, the space at infinity of a hyperbolic gadget is a fractal. Yeah? So this is a more precise formulation of what we have tried to motivate earlier. How do symmetries get in? So now we'll come to the third player of the game. What are symmetries? Symmetries are, formally these are what are called groups. Yeah. So basically there is a way of, you have a collection of, say, a collection of transformations of space, and you can compose them and you can invert various things. Yeah. So for instance, a collection of symmetries can be given a description as follows. So what is it? You have a collection of letters G1 through Gk, yeah, and now you look at all words, yeah. So the entire set of finite words that can be described given the generators G1 through Gk. So what do you, and I have already told you that you are allowed to invert particular symmetries, right? So you are allowed G1 inverse, you are allowed G2 inverse. So what is an instance? So think of a reflection in, say, an xy plane, vertical, yeah. So if you reflect, every point here goes back there, it goes to the other side. Reflect it back again, it comes back where it was, correct? So the inverse of this reflection is itself. Yeah? Now suppose you have a translation by distance d, yeah? Then what is its inverse? Translation back by minus d, right? This is all that there is to it. And you can, if you allow yourself transforms of this space at which we are sitting in, then it's a composition of all these gadgets, right? Things which preserve distances in Euclidean three-dimensional space is an example of a group, right? Okay. So, how are you going to describe it in the simplest possible terms? You have some finite number of symmetries, and then you are going to take all compositions of these. So that finite number of symmetries which you start off with is called the generating set. That here is this G1 through Gk. Yeah? It has certain words, actually, not just G1 times followed by G1 inverse, but certain other more complicated words could give you back the trivial element. Yeah. So assume that again that this is generated by some finitely many guys. These are called the relations R1 through Rs. Yeah. So for instance, suppose I reflect through 90 degrees along the xy plane. Yeah. Reflect along the x-axis, reflect along the y-axis. Yeah. Now reflect along the x-axis, again along the y-axis. So you have actually done, you've come back to it, to where you started off with. So what does that mean? X, suppose you call that first generator G1 and the second reflection G2. Then G1 times G2 times G1 times G2 is again equal to 1. Right? So that is an example of what I have marked here by R1. So suppose there are finitely many such relations R1 through Rs, which along with these generators generate for you all the relations that are there in the group. Yeah. So G1 through Gk generate, and the words that are trivial are given by R1 through Rs. Right? So this is called a generating set. This is called a presentation of the group. So for example, suppose you have the group Z consisting of integer translations, and you have another group Z consisting of integer translations, but now in the y direction. The two fellows together generate for you the group called Z plus Z, right? So there is a generator, say A here and a B here, and then A and B would be equal to B times A, right? Translating vertically followed by translating horizontally is the same as translating horizontally followed by translating vertically. So the group Z plus Z of all integer translations of the Euclidean 2 plane, that has a presentation A comma B with one relation AB equal to BA. Alternately, AB, A inverse, B inverse equal to 1. Okay? So that's what I mean by these generators and relations here. Corresponding to any finitely generated group with finitely many generators, there is a graph. Yeah? Enter geometry into the picture. Purely algebraic gadget. Yeah? From that we extract geometric information. How? You construct a graph where the vertices consist of all the elements of the group. That means all the compositions of G1 through Gk. I have drawn here a particular example where there are no relations. This S is 0. Yeah? R1 through Rs, the set is empty. Yeah? So you have just two generators, A and B, and no relations. Which means what? All words in A and B are where you only restriction, you don't follow a letter by its own inverse. Then you get different words, right? So for example, SEA and SAE, yeah, they are distinct words, right? So restriction of it's a failing of the English language that SAE does not mean anything there. That's not a problem here. Here we are looking at formal concatenations of symbols, okay? Alright, so here what are we looking at? We are looking at the alphabet consisting of two letters, actually four. Identity is something, A, B, A inverse and B inverse. And the only thing that we allow is A followed by A inverse is trivial, B followed by B inverse is trivial. Then what is the graph? The graph consists of, the vertex set consists of all the elements of the group. The edges are pairs of group elements such that A inverse followed by B is one of the generating set, right? So here you have, let's say this is G1 and this is G2, yeah? So what are you doing? You are looking at all formal words in G1 and G2. So you have, I call them A and B here. So it's A, then this, so if you want to go from here to here, it's A, and then this guy is B. It's going up by B, right? So this word from here is A, B. If you went straight, it would be A, which is A square. If you were to go down, it would be A, B inverse. Correct? So what are you doing here? For every vertex of this, so this is called the free group of generators. Free means there are no relations. Yeah? So Z plus Z, the group of integer translations of the Euclidean plane, is not free. Yeah? In particular. This is what's called a free. It's an example of a free abelian group, but that's a completely different issue altogether. So here, what are you doing? For every vertex, you're putting a for every element of the group, you're putting a vertex, and if they differ by one of these generators, you're putting an edge. You're constructing a graph, and if you are the free group, if there are no relations, a relation exactly corresponds to a loop. There are no loops. So this is a tree. Okay? So the free group, which means that the group generated by say k, let us G1 through gk, here k is equal to 2, and an empty relation set, R1 through Rs is not there, empty set. Yeah? What you would get is a tree of valence 2 times k. K is equal to 2 here. So its valence is 4. A regular 2k adic tree is what you would get. Yeah? So what would that mean? Now assign each edge length 1, you are going to get a geodesic metric space. You get a metric space where you can join any 2 points by straight lines. So from an abstract group given by generators and relations, you have extracted a geometric space. You can ask whether that is hyperbolic or not. Correct? So from groups, discrete groups, a geometric space, and then impose hyperbolicity on it. Yeah? So the question now, then this becomes, so this graph is called, it's got a specific name, it's called the Cayley graph of the group. Yeah? This is founded by this mathematician Cayley, long back. Yeah? So if you have a finitely generated group such that its Cayley graph with respect to that finite generating set is hyperbolic in the sense that I had drawn here. Every side is contained in a neighborhood of the other 2 sides. Then that group itself is going to be called hyperbolic. Yeah? So it makes sense for a finitely generated group to be something that is hyperbolic. Why? Because the path from algebra is through geometry. Yeah? Okay? And if you look at this Cayley graph carefully enough, you will see that the boundary is exactly what we had in that tree that we had seen before. So the boundary is a fractal. So here's a general fact. General fact is that this F2 means free group on 2 generators. Boundaries of hyperbolic groups, which means that if you have a group which has this hyperbolic geometry, then the boundary is also a fractal. Okay? So this is the general feature that is going on in this. The trees are actually, they don't quite follow a group law, they follow something like a quasi-law, but something like this happens there also. Alright, that's one feature. Let's try to give some more pictures of groups and geometries arising from them. Take a triangle. Yeah? This is an example of what is called a hyperbolic plane. I will not define what the hyperbolic plane is now, but I hope some of you have seen paintings by this artist called Escher, Maurice Escher. Have you seen paintings by Maurice Escher? Anybody? No? Okay, fine. So there was this artist called Maurice Escher who used to take formal mathematical structures. Let's go one slide further. Maybe you'll recognize this picture. Have you seen this picture? Yes? No? Okay. How many have seen this picture before? Okay, so it's a non-empty set. Good. Okay, so he had drawn a whole bunch of pictures of what are called tilings of the hyperbolic plane, and then there are these various pictures. They're called heaven and hell pictures, fish and birds pictures. Anyway, whole bunch of them. So what's going on here? You're taking a 2-dimensional disk, yeah, and you're imposing on that a certain geometry. And this is really how hyperbolic geometry came to be discovered in the 1820s, yeah. So what's going on is that you make the sum of the angles of the triangle strictly less than 180 degrees. Yeah. So what is the triangle that's happening here? You look at, so at this point it's a right angle. Okay? This angle here in the black, say look at the black triangle here, this angle is 90 degrees. So if you reflect it 4 times, it becomes the full dimensional plane locally, right? Here, there are I think 1, 2, 3, 4, 5, 6 and 12. So this angle here is 2 pi by 12, that's pi by 6. Angle here, each angle is pi by 6. So if you rotate it 12 times, you're going to get 2 pi. Yeah? This angle here, there are 8 of them. So that is 2 pi by 8, that's pi by 4. So you have a triangle in this geometry where the angles are pi by 2, pi by 4, pi by 6. sum it all up, it comes to less than pi. Yeah? But you can still have, what are the, now think of it formally. Reflection squared to identity. Yeah? These are these generators, A, B and C. What are they? They are the reflections in the three sides. This side, and this side. Yeah? If they are reflections, then they are their own inverses. A square is equal to identity. B square equal to identity. C square equal to identity. Those are these first three relations. Yeah? But there are things around vertices. Around this vertex is reflection along A followed by reflection along B. Then twice. Right? So AB is equal to identity. That was this reflection in the x-axis, reflection in the y-axis, reflection in the x-axis, reflection in the y-axis. You come back where it was. That's this AB square. Now you look at this pi by 4 guy. AB, it's reflection one, the first one is B, the second one is C. So if you do BC 4 times, then you come back. That's this word here, BC to the 4 is identity. If it's around this vertex, it's 12 guys are there, 2 different reflections, C and A. So that's CA to the 6. So this particular picture here is an example of a tiling of the unit disk by triangles which have non-Euclidean angles, and you get a pictorial representation of this group. Yeah? So what's happening is that the tiles are two-dimensional and the boundary towards which it is accumulating is a one-dimensional circle. Yeah? This is an example where you have two-dimensional hyperbolic geometry inside. If you were a creature living inside this plane, then one would recognize the geometry around oneself as intrinsically hyperbolic. But if you have an intrinsically hyperbolic geometry in dimension n, somehow at infinity on the boundary you should have fractal geometry of one dimension less. And here you have the simplest possible fractal geometry, which is that of a round circle. Yeah? It's a misnomer to think of a fractal as necessarily fragmented. Yeah? Very smooth objects are things which are not fragmented at all. Yeah? So those are examples of fractals. It's just that smooth objects are examples of fractals. Fractals are not examples of smooth objects. Okay? That's how it goes. That's how the logic goes. Alright. So this is an example. And this picture of Maurice Escher is doing exactly the same thing. How much time do I have? 10 minutes? 15. It's okay. Alright. So, let me pick up my... Yeah, so this picture of Maurice Escher that we've drawn here, so this picture of Maurice Escher that we've drawn here, that's an example where you have, I mean, yeah, so basically the eyes and the actual anatomy of the fish is irrelevant to the geometry. So what's happening is, again, you have triangles, and then this square has not been divided into two. There is a diagonal here. So this is a tiling of the hyperbolic plane using triangles, yeah? And then of course he's given an artist rendition by drawing in pictures there, pictures of fishes there. Alright, good. Now, so what have we so far? Suppose you have a group, collection of symmetries, algebraic gadget, from which you extract a geometric gadget, the Cayley graph, demand that that is geometric, right? So then you have the notion of a hyperbolic group. Try to illustrate that given any hyperbolic group, it has a space at infinity, which is a fractal. Yeah? Now we pass to the relative problem. What's the relative problem? You have a hyperbolic group. Sitting inside it, you have another subspace, a subgroup, right? Which means that it has its own law, own set of symmetries, own set of generators and relations. Suppose that fellow is also hyperbolic, right? So what are you thinking of now? You are thinking of a subspace which is hyperbolic sitting inside a hyperbolic space. Alright? For example, suppose you have these tendrils sitting inside a leaf. A leaf is a two-dimensional gadget. inside that you have this collection of tendrils. So you have a one-dimensional structure inside some two-dimensional space. That's the model problem that we are talking of. Suppose the intrinsic geometry of the one dimension is hyperbolic. It is so in the case of the tendrils inside the leaf of a tree. Yeah? And the ambient geometry is also hyperbolic. But the question that we are asking is, how does the hyperbolic geometry of the sub-object interact with the hyperbolic geometry of the ambient object? Simplest question, does the inclusion, so suppose formally what are we saying? You have a subgroup of a group, which means a sub-algebraic structure of an algebraic structure. Suppose that the geometries are also hyperbolic. Yeah? That's what it means by saying that the subgroup is hyperbolic. Then you have an inclusion of the Cayley graphs. You have an inclusion of the geometries. The algebraic structure includes, the geometric structure includes. Question, what happens at infinity? Yeah? So from the geometry we want to go to the fractal. Yeah? So the question that's posed is, does the inclusion map extend at least continuously to the fractal geometry of the boundary of H to the fractal geometry of the boundary of G? Yeah? Geometries include, do fractals interact nicely? In general, they cannot be inclusion of the fractal geometry on the boundary. This is a fact, not too hard, but it's a fact. Question is, does it at least interact without tearing apart? Yeah, so I mean, if you have, what do you mean by a continuous function, say from an interval to some space? It means that you've not taken a map of the string without tearing it is a continuous map. If you tear it, it becomes discontinuous, right? So what we are asking is, you look at the fractal boundary of H as some space. From there you are mapping it into the fractal boundary of G. Is this map continuous? That's the question that we are asking. Yeah? When you have the most natural inclusion of this hyperbolic subgroup of hyperbolic. Answer in this generality is no. This was answered negatively. A counterexample was given in 2013. Fairly recent, but the question was asked about 2 decades back. Anyway, however, the classical situation, there is a classical situation where the fractals and the spaces are fairly well behaved. So think back to that picture I had shown you briefly by showing there's a sort of a blue plane here, a three-dimensional space sitting above it, and some very ornate kind of ornaments on the plane. So that's the geometric situation, which is really the three-dimensional nicest hyperbolic structure. And in that case, the question was really swung back by another mathematician called Thurston. So in this generality, hyperbolic substructure of a hyperbolic structure, does it extend to fractal inclusion into fractals? Answer, no. Relatively recent counterexample. But the classical problem was, suppose the group G is hyperbolic and it acts by symmetries on the archetypal model of hyperbolic geometry in 3 dimensions, which has a name. It's called hyperbolic 3 space. Yeah? What it is, I'll say in just the next blurb. Yeah? What happens in this situation, in this very classical situation? This is one of the motivations for giving this abstract definition of a hyperbolic group. So what is hyperbolic 3 space? So you think back to high school, where how did you compute lengths of curves? ds square equal to dx square plus dy square. Yeah. What does that mean? It means you given a curve, you have xt, yt, a parametrization, right? Then dxt, what is it? X prime t dt. Square it. So x prime t square plus y prime t square root times dt integral over t. That gives you length, right? So if you do the same thing in x, y, z coordinates, is dx square plus dy square plus dz square. What is happening here? What is 3-dimensional hyperbolic space? It's the same thing, but now it's no longer Euclidean 3-dimensional space. It just take the upper half space. Yeah. So z greater than 0. Yeah. You put the metric ds square equal to dx square plus dy square plus dz square, whole thing divided by z square. Right. So you're going to do the So you're going to do the same computation, x prime t square plus y prime t square plus z prime t square whole divided by z of t square, then square root times dt. That's how you're going to compute lengths. That's all. It's a multiplication by this one little factor z square. Where does this z square come from? That's a completely different story. Yeah? That I will not have time to go into today. So what happens is that if the action, so what is the situation here? You have a subgroup H acting on this three-dimensional space. There is a certain sense, take it on faith for the time being, that this H is the archetypal model, the classical model for hyperbolic geometry, for three-dimensional hyperbolic geometry. Now you have a group acting by symmetries on this space. Yeah? If you have a group acting by symmetries and nicely, so for example, what is nice action? Nice action is a certain sense in which you can pass to a quotient by that action. So what does that mean? I'll illustrate it in a moment. So what does it mean to pass to a quotient of a space by a group of symmetries? Here is the instance. So you have integer translations acting on the Euclidean plane. Yeah? If you look at one of these squares here, if you have one of these squares here, unit squares here, say from 0, 0, 1, 0, 1, 1, 0, 1. You take this square tile. Yeah? All of you have seen floors tiled by square tiles. That I am absolutely certain of. Yes? Very good. So now you look at this square tile, you look at integer translations. If you take this one square tile and you translate it in this direction, you are going to get this thin strip divided into unit squares. Now translate it in the vertical direction also. You are going to get all of R2, all of Euclidean 2 plane tiled by squares. What does it mean to pass to a quotient? It means you take any point and its orbit under the z plus z action and identify to a single point. How do you do it geometrically? Take a small square here. Then what does have the translations of this unit square is the whole plane. So I can just focus on this two-dimensional square here. And then, but what happens is that the bottom edge gets identified with the top edge. The left edge gets identified with the right edge. So I identify those two places. Yeah, identify these, put glue and paste them together. What do I get in the process? So the quotient space that we get is this two-dimensional torus, the surface of a donut or a surface of a bicycle tube. Yeah? So that's what's meant by quotienting. Go back to the problem. Here's a nicer example. So this two-dimensional hyperbolic plane that we had talked about, disk, yeah, spanned by various triangles. What you can do is now tile it by octagons. Yeah. So here what's this an example of? This is a pentagon. All these angles are right angles. So you flip four of these pentagons together. What you're going to get is an octagon. Yeah. And if you take an octagon and do the spacing, you're going to get two of these bicycle pipes tubed together along this fat waist here. What? Between what and what? The previous guy is a genus 1 surface, this is a genus 2 surface, they are not diffeomorphic. So anyway, whatever it is, so what I am saying is that you look at this octagon and then you pass to the quotient, you're going to get something like this. I mean, this is what, it's a pretzel or... Anyway, there are these naturally occurring objects also. So I think if you have three of them together, you call it a pretzel. You have some of these things, snacks that come in packets nowadays, which look like this. Yeah. All right. So this is a genus 2 surface. This is what it is. Mathematicians don't have this kind of a romantic view of things, so they call things by much more staid names. So this is called a genus 2 surface. The previous fellow is called as genus 1 surface, so on. You boil it down to sort of the minimalistic notation. Okay, good. So this is an example where you have a hyperbolic plane and a group of symmetries acting on them, and you pass to a quotient. Fair enough. Now let's return to the three-dimensional problem, and I think I'll just have time to make the statement. So you have a discrete, now you have returned to the the classical problem that was posed by, I said it was posed by Thurston. You have a group that acts discretely, which means that every point is transmitted away from it by a definite distance, and so it acts by isometries, which means distance preserving maps, but now the metric is dx square plus y square plus dz square by z square instead of just dx square plus dy square plus dz square. That's the only difference. Yeah. This group of transformations, and here I'll beg your indulgence a little bit, it turns out to be the same as the simplest set of complex analytic transformations that you look at. Yeah? So if you have z greater than 0, what is z equal to 0? Z equal to 0 is the xy plane. Xy plane can also be identified with complex numbers, right? X plus iy. But as soon as you have this x plus iy, then there's a certain natural set of transformations of the complex plane union the point at infinity. The complex plane union the point at infinity is called the is called the Riemann sphere. So that's C is complex numbers, hat is C union infinity. Yeah. What is the most natural set of transformations of that sphere? It's what are called the set of Mobius transformations, z going to az plus b by cz plus d. Okay? What are called fractional linear transformations and so on. This can also be identified with 2 cross 2 matrices over complex numbers of determinant 1. Yeah? Actually, it's quotiented out by a certain thing, that's why there's that P, but otherwise it's called PSL2C. This is also equal to the set of distance preserving maps of the hyperbolic 3 space. Yeah? So you have various different descriptions of the same gadget. Hyperbolic 3 space, which is that particular metric, mysterious metric, that has a geometric object has isometries, distance preserving transformations. That's what gives rise to all these congruences that we studied in school. Angle, angle, side, side, angle, side, 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 etc., etc. Yeah. So they all that it means is that you can transform one angle to another by isometries. Okay. So that's the geometric way of looking at this particular set of symmetry, this group. Alternately, you can look at a matrix group. You can always multiply and divide matrices, matrix inversion, etc., etc. So you look at 2 cross 2 matrices over complex numbers determinant 1. That's roughly PSL2C. That's SL2C, but there's a little difference. Alternately, you can think of conformal transformations. Conformal means angles are preserved, circles go to circles, which means here in this case you are looking at conformal transformations of the Riemann sphere, complex plane union infinity. Yeah. So when you pass to the quotient, you are passing through the quotient of the geometric gadget. Yeah, hyperbolic 3 space quotiented by a group of symmetries acting on it. This group of symmetries is also called the fundamental group of the quotient object. And the sphere is the ideal space is the space at infinity of hyperbolic 3 space. It has a natural set of transformations given by a complex number z going to a times z plus b by c times z plus d. Yeah. So now you have two different descriptions: geometric description in H3, complex dynamic description on the boundary C hat. Okay. And I think I just have time for this theorem. What the precise form of this theorem is going to become too technical. There is an exact dictionary between the dynamics of the group on the Riemann sphere. This is exactly where the fractal comes in. And the geometry of the quotient, hyperbolic 3 space by G. This is where the hyperbolic geometry is. Okay? So the theorem says that you can either look in 3 dimensions and you have this nice geometric quotient and look at subtle geometric invariance of that, or you can go to the boundary and in one less dimension you can study dynamics. That's going to give rise to certain chaotic phenomena. This chaos is there now in complex analytic dynamics on the boundary. Yeah? The theorem says that whether you are located at infinity or whether you are located in the geometry inside, you have the same amount of information. There is an exact correspondence between them. So this theorem is a result of the work of a bunch of people. So part of this theorem was due. Okay, so I'll stop here. Thank you.
Mohan Maharaj took us to the depths of fascinating world of hyperbolic space. Many of you in the audience may have some questions or further clarifications from Mohan Maharaj. I hope Maharaj, some questions you can take.
Yeah, of course.
Please.
Sure.
Anyone
I
of
would
you?
have been very happy with questions during the talk. Yeah, go ahead. Yeah.
We are in the nature and we can up to till now during my study personally that we can explain everything by 3D geometry, 3-dimensional Euclidean space. So why we
Really,
need
you can explain this?
means
Why does a tree have this fractal structure? Can you explain? Can you explain my three-dimensional geometry? I have a theorem which says that you cannot. Now, what do you mean? See, the thing is, so here is the question that you. This is not a question that you can answer or I can answer. It's a problem that was posed by Euclid in 200 BC. It required something like close to 2000 years to address. What is the problem? Simple problem. You have all seen the axioms of Euclidean geometry, yes? Points, then straight line segments, then bi-infinite straight lines, angles, all right angles are equal, the existence of circles. 4 axioms. You have a 5th guy which is not called an axiom, it's called the parallel postulate. Okay? Euclid's problem was, can you prove the 5th postulate from the first 4 axioms? On question. Yes or no? Can you do it with your study of Euclidean geometry?
during study we have said means you just accept it, then we can progress.
Why the science starts with not accepting. Okay? What is given to you? If you want to probe deeper, yeah? If you want to probe deeper, you can't accept. I mean, why is this true? Okay. So answer is actually you require a huge amount of machinery. And the answer to it was given by Gauss in 1828 or 1825, there 1824. 1829, Janos Bolyai, 1829, yeah, I think it was Janos Bolyai, 1831-32, it was Lobachevsky. Simultaneously, one person in Hungary, one person in Russia, independently discovered, yeah, that the 5th postulate can be replaced by some modification. And the geometry it gives rise to is hyperbolic geometry. Okay? A solution of that kind in later years due to Poincaré gives rise to that metric there, that dx square plus dy square plus dz square by z square. Okay? So, by looking at 3-dimensional space, I claim, and I have enough examples to fortify this claim, that you cannot explain even Euclidean phenomena. Yeah.
Sir, I have 2 questions. The first one regarding this, that all the 3D information.
Just one more very important example, because this has come up. So, for example, you've heard of relativity, right? Yeah? You are using this gadget called a mobile phone, correct? Have you used a GPS ever? Yes? Okay. What does that GPS use? Can you explain this is complete technology, this is a technological institution. This is a nice question. What is the technology behind the GPS? What is the science behind the GPS? So the GPS uses in order to predict a road, that you are going on to such and such a road, it has to have a map of the whole geometry of the earth. Yeah? For that you need, if you used only Newtonian mechanics to do that prediction, yeah, after traveling maybe 100 miles, maybe 1000 miles, you will be off by one road. Why? You need general relativity corrections to do that. What is general relativity? Where does what geometry does general relativity rest on? It rests on something called Riemannian geometry, where with this form that I had given here, dx square plus dy square plus dz square, without that z square at the bottom is Euclidean geometry. But you have factors there, arbitrary factors, that is called Riemannian geometry. Discovered 60 years before Einstein by Riemann. Gauss, who discovered hyperbolic geometry, was the thesis examiner when Riemann presented this, 1854. 60 years later, 1905 to 1950, that's around the time where general relativity came into existence. 1 century after that, we are using it today without knowing anything about what has gone into it. Yeah. All right. Go ahead. Yeah, you have a question.
Sir, my first question is about this. The information contained in the three-dimensional space is stored in the surface in the form of fractals.
Yes. So this is a very, very specific kind of a theorem. Yeah. It's not a general theorem. In this particular context of hyperbolic free space versus complex dynamics, answer is yes, it is continuous.
There is a similar, we can say, analogy happening in black holes.
Absolutely correct. Absolutely correct. Absolutely correct. So there is a field of string theory. This was discovered in 97, 98 thereabout. Somebody called Juan Maldacena.
Yes.
Yes. So he started off something called the ADS CFT correspondence. ADS, you are in physics?
No, I'm from fluid
Do you
mechanics.
know what Wick rotation is?
No, sir.
So basically, if you have something, if you have ds square plus dx square plus dz square minus dt square is your Lorentz metric. Yeah. So minus dt square you write as plus I times dt prime square. Yeah. Now you replace that I dt prime as a different variable. Yeah? dw. Now that is called Wick rotation. Basically converting something which has a minus sign by replacing minus 1 by square root of it's square root of minus 1 whole square. Yeah? And then replacing this complex variable by a real variable again. That's called Wick rotation. Yeah? So if you have ADS, Wick rotate it, you're going to get hyperbolic free space.
The information is stored on the surface of the black.
Correct. That's what I'm trying to tell you. So this is also an example of that duality, of that same ADS CFT correspondence is a conjectured reality. Yeah, and the dynamics is in some ways much simpler, in some ways much more complicated, because the dynamics of the group that is being considered is a simple group, real line. But the system for which the dynamics is being considered is a much more complicated system. It's some quantum evolution of some states.
The second question is going to you discussed in the initial part of the lecture.
Yeah.
That is about that in order to maximize the accumulation of sunlight, the foliage tries to grow in a fractal structure. To look into the inside the leaf, we have this again the fractal structure that. The continuous division is going on,
but
to optimize the supply,
the
supply of nutrients, right?
Correct.
So now I am from fluid mechanics and I study turbulence.
Yes.
So I applied this concept that
yes.
the dissipation has to be optimized, and the supply of nutrients is like dissipating the nutrients to the entire leaf. So when I applied to the turbulent velocity signal, it turned out to be a tree.
Okay, very good. I have no idea why that has happened, but
what I wanted to ask is, these are all static structures. The branches do not change; they remain the same over time.
Yeah.
Now, in the flow, the things change.
Dynamics,
so the tree grows.
Correct.
The tree grows with time, and we have all the data sets of 4 minutes, and the tree is like this big and grows.
Correct statement.
So the branches are not triadic; they're dyadic, because three things cannot exist in the flow, because you said the relations. The relations defined were defined by me, because we have to understand.
No, that is a simplification in this case.
So we can adopt any relation.
Yes, absolutely.
So
this I have given only a relation up till the second stage. There are group theoretic versions where you can put in 3-dimensional cells, 4-dimensional cells. See, mathematicians do not respect this human limitation of being everything visible up to 3 dimensions, right? So n is not particularly. I mean, up till dimension 3, somehow some theorems become very, very interesting. But yeah.
So what we observed was that due to the dyadic branches, so the trees were very asymmetric, and it told a different. So information was presented to us through a tree in a different way that we
very
could
good.
not.
Excellent. Very good. Yeah.
Next question.
Yeah. Speak loudly.
I have two questions. First question is, as per my understanding, what you have discussed, that fractal, all the geometry is more or less very simple to understand. It is getting bifurcated, or the size factor is getting diminished.
Yeah. So what I did was,
let me
clarify one thing.
Yeah.
the geometry of the tree that I had started off with is the simplest possible example of hyperbolic geometry. Yes, I have not discussed more complicated things except for that picture of Escher. The one person raised his hand about this picture of Escher. Who was it? You were the person.
Yeah.
So that is an example of a two-dimensional hyperbolic geometry. Hyperbolic geometry exists in all dimensions. So I have given you the two simplest examples, and I have said something about the first interesting complicated example, which is in dimension 3. I have not drawn any pictures there.
Okay, this is what is there the term chaos in that? Because as far as my understanding,
okay. I'll tell you very precisely.
There is no chaos as per my understanding.
All right, I'll tell you what that chaos is. Suppose you have an infinite group, yeah, acting on a compact space. In this particular case, the Riemann sphere. You have an infinite group. Okay, so a point is going to have an infinite orbit. That orbit is going to accumulate on some set. Take any point on that set on which this orbit accumulates. Take its orbit under the group. Yeah, is going to be dense in that accumulation set. That means what? Simpler. Let's simplify this example. You have a flow line. Yeah, say a drop of ink dropped in some fluid that flows, and then there's a whirlpool formation, and then it goes round and round in some circle. Let's say. This is a very, very simplified cartoon of the kind of chaos that's going on here. Now you look at a point on that circle and you allow it to flow under the same whirlpool thing. What it is going to be dense in that whole circle? No, I'm not going to allow it to be sucked inside. I'm saying it's just flowing on the boundary of that whirlpool. Okay? Here something similar is happening. There is something called a limit set, which is the collection of accumulation points of a point on the Riemann sphere under the action of this group. So the limit set is a collection of accumulation points. Take a point in the limit set. Its orbit is dense in the limit set, which means what? You move from your point very slightly. You have no idea where it will land after some number of iterations. That's exactly what defines chaos.
Second question is, what you said was that the stem and branches.
Correct.
If you take a banyan tree, the things are quite complicated. There, it doesn't obey whatever you say.
Perfectly true. That tree, I was talking about a mathematical tree, where we have nothing whatsoever to do with it.
Thank you.
So actually, here's the point. I mean, this is the thing. We abstract out the shape of the earth, call it a sphere. And then you say that the earth does not satisfy such and such properties that a sphere is supposed to satisfy. So much the worse for the earth, yeah? The sphere satisfies it.
Okay. Any other question? Yeah. We can take couple of questions more. Yes. Yeah. And last one is there.
Good evening, sir.
Yeah.
So I am from Civil Engineering Department, and I wanted to ask that the normal mensuration problems that we apply in the Euclidean space for normal geometric structures like triangles,
yeah,
we do survey on practical land
correct,
areas,
correct,
so
correct.
we do triangulation.
Yeah.
So calculation of area for those kind of triangles, is it the same for
No,
Riemannian?
they're very different, very different. So the area is going to be strictly less than pi, right?
And so the calculations are for Riemannian triangles and all those, are they more simpler or?
No, they are much more complicated. Let's see, finally if you want to do, you have to resolve it, you have to do this. The difference is between 200 BC and 2000 AD. Why? Because in order to compute the area of a triangle, what do we do in mensuration problems? The area of a triangle, just a triangle, it's half base into height, correct? What is the corresponding thing here? The same thing is going to hold at an infinitesimal level. So if you have a square which is dx times dy, yes, you can do this Euclidean approximation. That's how we do it in Riemannian geometry. You break it up into infinitesimal pieces, then run an integration.
So what is the use of this kind of geometry for practical
So for
purposes?
example, what is the area of this gadget? If
So
you have
simply we can do length into breadth and find out the area. So what is the need?
suppose you had some wavy thing here, acoustics, yeah. So for designing certain things, a flat piece is not acoustically the best thing. Even simpler, you take a particle. Suppose you have a slope, yeah, and you have some friction on that slope. What is the slope that will minimize the passage of time from point A to point B? That is some particular geometric space. It's not the straight line, right? So those shapes do come up in nature.
Okay, so thank you.
Sir, in that first tree diagram, in that first tree diagram, like what we are doing this series convergence at 1 plus half and so on and so forth. So like if we go in higher dimensions for this, like any sort of convergence, does this also hold true? Like for example,
What do you mean by going in higher dimensions?
I mean like in this tree, we are like this is a two-dimensional figure. So like for example, in a three-dimensional figure, if we go, so does like the area of the triangles in that diagram that you gave. So like does a
Which diagram?
That circular one, sir.
Yeah.
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 So like if we add up the areas consecutively.
No. That's not what's going on. What is going on is just edges. I mean, so what's going on is the following. In the two-dimensional, I'll illustrate what is going on in the two-dimensional picture. So you have this graph. So basically, that two-dimensional is a collection of tiles, right? And now you construct a graph out of that set of tiles. What do? For each tile, you choose a vertex. If two tiles are adjacent, if they share an edge, you draw an edge between them. Yeah. Basically, it's constructing a graph dual to that tiling. This is what it's called. Okay. Now what do? You have a graph. It's an infinite graph. Now, given any infinite graph, you can perform this operation. You choose some vertex as your origin. Look at the edge, look at any edge in that graph. Look at a vertex which is at minimum distance. So there are two vertices on its two sides, right? Look at the vertex which is closer to the origin. Suppose the distance is n. Then scale that particular edge by 2 power n. Or lambda power n, where lambda is greater than 1. Okay? This thing can be done in arbitrary dimensions.
Thank you, Mohan Maharaj. We don't have much time to continue this session formally. Many of you may have some other questions or discussions with Maharaj. Maharaj will be there for some more time. So after this particular lecture session, you can interact with him. Words fall short to appreciate the erudition that Mohan Maharaj has depicted today. The acumen as a teacher was at his best displayed today. He was almost a teacher for all of us. And he took us to the depths of, as I mentioned earlier, hyperbolic space. We appreciate that Maharaj has agreed to come over and give the second Ramanujan Memorial Lecture with more than half a century publications, and he has a lot of academic visits to make across the world. And I know that during last 5-6 years he has almost 30-40 visits to different countries to give lectures, to teach different courses, and we are fortunate that this is the first visit of Mohan Maharaj to Iiests Shibpur, and we hope that we all have gained much because of the deliberations or lectures that we had today from Mohan Maharaj. As a token of appreciation, as a token of gratitude on behalf of Iiests Shibpur, I will request Professor Gautam Bandyopadhyay, member of Board of Governors of Iiests Shibpur and Professor of Electrical Engineering, to hand over a token of honor and gratitude to Mohan Maharaj. Mohan, can you please come over here? And I think we can conclude the session here itself with, again, we can join our hands to in appreciation of Mohan Maharaj. Thank you very much.
Back.